Thank you. It's nice to be here, and it's an honor to be a colleague of Raghu Varadhan. So this talk is about rare transitions in noisy heteroclinic networks. The whole theme is small noisy perturbations of dynamical systems. So I will be talking about stochastic differential equations like this. So B is the drift. It's going to be a fixed drift. And epsilon is a small coefficient in front of the noisy term. So epsilon will go to 0. Most people know about the classical Freiden-Wenzel theory. So the keyword is metastability. And that's the situation where you have multiple potential wells or something, and the system makes extremely rare jumps between them. In this talk, I will describe a class of systems that exhibit sort of similar behavior, but transitions between different metastable states are much shorter. So we will also see a certain hierarchy of clusters and a cascade of transition times. And these transition times are of this order of magnitude, unlike this one. So it's based on this preprint. It's not that we completed it yesterday. It's already accepted in the memoirs of the AMS. But it's a long paper. And so I still feel entitled to bother people with talks about this. So what is a noisy heteroclinic network? Narrowly speaking, it's a feature of the phase portrait of a dynamical system generated by the drift B. And that feature is that there are multiple saddle points, like these are all saddle points. And the saddle point is a critical point that is a 0 of the vector field. And locally, the dynamics looks like there are stable directions and there are unstable directions, right? So for this one, this is the unstable direction. This is stable direction. So you have a whole bunch of these saddles in the situations that I want to consider, and these saddles are connected to each other by heteroclinic orbits, heteroclinic connection. So heteroclinic connection is a trajectory of the dynamical system. So if you start somewhere in it and run the dynamics forward, you approach the next saddle. And if you run the dynamics backward, you approach the previous saddle. So this is a planar example. This is an example in 3D. So actually, there are many good examples. And in this talk, I will mostly, partly for pedagogical purposes, partly because some of our theorems work in all dimensions, some are restricted to low dimensions. But in principle, these things occur in any dimensions and in infinite dimensional situations. So my journey into this started with neural models because I attended a talk by Fraimovic who talked about neuronal models and sequential decision making. But there are lots of other interesting models. Now these things, they look fragile. It seems like you perturb a little bit and things fall apart. These arrows do not meet the saddles. But it turns out that under a class of meaning of conservative perturbations, these things actually survive them. And I'm going to show that on the next slide. And moreover, if understood more broadly, if these do not have to be point saddles, if they are, they can be attractors, they can be cycles and stuff like that. So then this becomes a ubiquitous feature in high-dimensional dynamics. So this slide is meant to demonstrate that if there are certain symmetries in the system and maybe some conserved quantities, then it's so easy to break down this the heteroclinic structure. So if a perturbation of a system like this preserves this plane and this plane, then this heteroclinic cycle survives small perturbations. So it's a robust feature. Now this is a slide that I copied from this paper, And this is supposed to show that in high dimensions, instead of saddles, you can have whole heteroclinic, or pardon me, whole cycles, right? So this is an example of two cycles in a special case of three-body problem, and these occur a lot in celestial mechanics. So each of those, it plays the role of a saddle. So there are orbits connecting these periodic orbits to each other. And if you go into high dimensions, things become really messy, as we all know. But this is an example from hydrodynamics. So this group was busy actually finding finding stationary solutions and periodic solutions for the plane coed flow. So this is basically the Navier-Stokes system between two moving plates, not in a very turbulent regime, but the result is that there are plenty of equilibrium points, stationary solutions, and also some trajectories connecting periodic orbits to each other. I mean, it's hard really to talk in detail about this picture, but these things, they really emerge easily in high-dimensional dynamics. For the rest of the talk, I will be talking mostly about these like more planar pictures, partially because that's what our theorems are most easy to explain with, but partially because some of them are written just for the planar flow. Okay, so I'm looking at this equation. I want to understand what happens when the noise is very small. And suppose you have a picture like this. So this is like a cellular flow. And suppose you start the diffusion right on one of those connections. And what happens next is that you sort of follow the heteroclinic connection. But once you reach a small neighborhood of the critical point, what happens next is the following. This is a critical point, so the vector field is 0 right there, and it is small in a small neighborhood of this. And so once you reach this, then for a while you will just be perturbing essentially the Brownian motion, the two-dimensional Brownian motion in the neighborhood of this point. But eventually, due to some inevitable fluctuation, you will get a little bit away from the equilibrium, either to the right or to the left. And at that point, the deterministic dynamics will take over. So you will get to some place where the drift is now not so small, and then you will follow that connection to the next point. And sort of the same thing happens, right? So you mostly follow this connection, small perturbations, small oscillations about that. And then at this point, you will also make a decision which way to go, up or down, and so on and so on. And so if you buy this description of what's going on, then you would think, aha, this is just a random walk on this graph, really, as epsilon goes to 0.
What is the drift doing within itself?
It's not. I mean, at this point, it's not important. At some point, I will have maybe to say that the dynamics is stable. Like these cycles are stable, so it takes a long time to exit into the bulk. Okay, so if you buy my description, then you will think that this is just a random walk on this graph. But it turns out that it's not what happens. So it turns out that as epsilon goes to 0, in the limit, the system has a limit in a sense, but that limit is not Markovian. So there's some memories retained about the past. And so these decisions that are made by the system, they are, in many cases, they are predetermined by the history of the process. And the first part of this talk, it's about these older papers where I show how this happens. So if I want to find how probable or improbable is for my particle that follows the diffusion to follow a certain path, a certain heteroclinic path, well, I may surround this path by these domains, and I can ask myself, okay, I start close to a point on one of those heteroclinic connections. Maybe there is a small perturbation in the beginning, and I want to ask what is the probability to exit, say here, through this edge, And given that, what is the probability to exit here and say not there or any other place, and so on and so on. And I want to understand also the distribution of the exit location. And this boils down to studying these domains one at a time and then iterating that result. And so here is a caricature of one of those domains. Well, it's not a caricature. It's a plot of one of those domains. It's planar. And this works in high dimensions as well. Right, so let's see what happens here. So this is the stable manifold, in this case just a curve. This is the unstable manifold. It's also a curve into the, I start close to, so this point x0 is on the stable manifold, and then there is a small correction. I assume it's of this form. It's epsilon to alpha. That's a normalization. That's the scaling. V is just this vector that's transversal to the stable manifold, and xi epsilon is a random variable, and let's assume that it converges in distribution to a limiting distribution. Why do I consider this kind of initial condition? So I want to ask myself, if I start with some scaling initially, what will happen at the exit? And it turns out that this form of perturbation is sort of invariant. So it turns out that the exit location, so tau is the exit time. And so my process at the exit time, as epsilon goes to 0, it has the following asymptotics. It still has the same form. You will exit with high probability near one of those 2 points, q plus or q minus. And also you will have a scaling around that. Epsilon to the new power instead of alpha, there's a new scaling that emerges, and it's just with some probability you get some scaling here, or with some probabilities you get some scaling there. This probability sum up to 1, and this random variable eta epsilon converges in distribution to a limit. And well, the nice thing about this result is that it has this invariant form, right? So you start with some scaling. After the process passes the saddle, you also get a scaling, and that means that you can iterate it from saddle to saddle along the entire sequence. So this is just one simple calculation that I want to show you. It's the main one for this talk. Now the actual content is quite technical, but this is a simple way to explain this. So imagine that things are very rectilinear, and we just have the unstable dynamics along the horizontal axis is governed by this equation, and the stable dynamics along the vertical direction is governed by this equation. So this is like Ornstein-Uhlenbeck process, but this is like the true one, and this is with a positive lambda instead. And well, I start in the vicinity of this point, and I want to ask myself, what is the distribution of the exit location on presumably one of these 2 lines? And so for that, because I chose the system to be so simple for this pedagogical example, you can solve this equation explicitly, right? So this is the Duhamel principle, variation of constants formula, and you can just write the solution explicitly like this. And I'm doing that for the first coordinate so that I can express the exit time from here. So at the exit time, the first coordinate, the coordinate along the first axis, it is equal to r in absolute value. So it's either here or there, one of those 2 lines. And from this formula, I mean, just equate that to r in absolute value, and you express tau, and you obtain this expression. And this sort of shows right away that the exit time has logarithmic asymptotics, right? So this is like log of this product is the sum of logs, and so the leading term is epsilon to the alpha, and then there is a correction. So maybe right away I should say that in principle I use the asymptotics of these exit times for some applications. I use this to decision making in psychology, and I use this for describing the incubation periods of various diseases. But I'm not talking about that. So I've chosen to go through this heteroclinic story only. So this is what the exit time looks like, and then I want to plug that this expression into the expression for the second coordinate. So the second coordinate also, you can write the Duhamel principle. It is useful to write it not just like this, but in a slightly different form. But in the end, if you combine all these things, you will end up with this expression, and this is sort of the main one for this talk. So what matters here is that there are two terms, and this one is essentially Gaussian. It's epsilon times a symmetric Gaussian random variable, and then something else, epsilon to the alpha rho, where rho is the ratio of the contraction and expansion coefficient times some positive random variable. And if I'm interested in the asymptotics of the exit distribution, basically I have to compare these two terms, like which one is more important. And so it means that I want to compare alpha rho to 1. So which of those gives higher contribution? And this leads to these two situations. So one is the strong contraction, where alpha rho is greater. So rho, remember, that's the ratio of the contraction coefficient to the expansion coefficient. And so if this is high, then this term is smaller than that, right? So it's epsilon to higher power than 1. And in the asymptotics, it's only this term remains. And so then the exit distribution is asymptotically symmetric, and moreover, it's Gaussian. And this is important because it means that at the next saddle, you will go with probabilities 1/2 down and up. So the symmetry of this exit distribution, that's what determines this. But this is not at all what happens when the contraction is not strong enough. So if the contraction is weak, then it's this term that dominates. And this one disappears in the asymptotics. And so this is a positive random variable times epsilon to alpha rho. And so essentially this is what the exit distribution scales like. And as epsilon goes to 0, you will most likely exit above the axis. And the size of this perturbation, epsilon to the alpha rho, is greater than the amplitude of the noise. And it means that the noise will not be strong enough at the next saddle to kick you down. So most likely at the next saddle, you will go up. As epsilon goes to 0, that probability of going up converges to 1, and going down converges to 0. And so this is this computation. What is the probability to exit down at the next saddle? So this is what your initial condition will be, because your exit distribution will serve as the initial condition for the next saddle. So you're starting at this point, and then there are noisy perturbations. So what is the probability that something like this is negative? So negative means it will go down at the next saddle. So this is a large deviation. So this is extremely small probability. Okay. So if I iterate this result that I just explained to you, then what happens is that I have a sequence of scalings, right? So there is a dynamic of scaling exponents. At each stage, I can compute what the how things scale. So I can compute exponents, and I can compute the distribution that scaling is in front of. And so it always has this form, and you proceed like that, except if at some point one of those exponents is less than 1, and you are maybe here, and you're asking for a wrong turn, so instead of going up, you want to go down. Asymptotically, this probability is 0, so it's unlikely to do this. And this helps me to classify all these paths into probable and improbable ones. And so it turns out that there's a certain vocabulary of pathways that will be realized by the dynamics, and some other they are extremely unlikely. So this is the example that I usually show when I talk about this. So imagine that you have this repeated structure. So this is the, you can view this on the torus. So you can think of this as the tessellation of the plane. So there are essentially just 4 saddles, and then they are multiplied. So there are reflections and periodicity. And let's assume for this example that the contraction is weaker than expansion at the first saddle, at second saddle, and the third saddle. So they are weak contractions, right? So weak contraction means that you will stay on the same side of the heteroclinic connection, right? So you already have exited, but you haven't had time to contract. That's what these the positivity of the limiting scaling law means. And so what happens here is that you start here, you will not contract enough to possibly exit here. So you will stay on the same side, then you will stay on the same side again, then you will stay on the same side. But then let's assume that at the 4th saddle, the contraction is so strong that it kills all the previous memory that you have accumulated. And so then here, despite the fact that you are pretty far now from the heteroclinic connection, so the contraction here will bring you back to the vertical heteroclinic connection. And it means that you kill all the memory here. The scaling here will become just epsilon to power 1 times Gaussian limiting distribution. And it means that here the diffusion will make one of the 2 choices with equal probability, 1/2 and 1/2, right? So this is the symmetric X distribution. So now it will decide which way to go, here or there. And once it does, it will follow the same story, here or there, here or there, and that's it. So at the times of this order of magnitude, at logarithmic times in the noise magnitude, you only have circulation within this simple complex of these two cells. At these times, it's extremely unlikely for you to exit in any of those directions. So you're just going to circulate here. Once in a while, you will switch. So this is actually a realization of the Bernoulli scheme. Every time you come here, you make an independent choice of which way to go. 1/2 here, 1/2 there. And that's all that happens at these logarithmic times. And this is a general picture. So at these times, you only have, like in multiple dimensions, it doesn't matter. I mean, you have to say something about, in multiple dimensions, there are multiple eigenvalues of the linearization, but you can say all the necessary things. And so essentially the result is that there is a small vocabulary of favorite pathways. And so the system mostly goes along these pathways and nothing else happens. And so this is known as heteroclinic cycling. But actually explaining this was what motivated me initially, because these people who were doing applications to biology, they showed me this process and they said, okay, it's weird, like, it's a high-dimensional space. There's a lot of freedom. There are all these arrows going all around the place, but the system always does only this and then this. But this, so if you believe that, if you buy this, the fact that you can model the system they wanted with these equations with multiple saddle points, then this is the explanation for small vocabulary of neuronal excitations that you see in those systems. But of course, this is only a description that's valid at this time scale, because it's a diffusion, it's an elliptic diffusion. So at longer time scales, it should travel all around the place. And so the question is, how does that happen? So after, so this was abandoned for a few years, but then I started thinking about this question, and so how do you describe longer time scales? So you want to, if you have a system like that, how do you describe the invariant distributions, or how much time does it take to go from here to there, stuff like that. So at this level, you cannot answer those questions. You need to quantify how rare are those rare transitions, right? I told you that it's unlikely to go like this, but how rare these transitions are? That's the question. And so let's make a preliminary computation. It's the same system that I have shown you, and let's assume that the contraction is weak, right? So the coefficient of contraction is not strong enough to make this quantity greater than 1. So this is what the exit distribution looks like. It's one-sided and scales as epsilon to the alpha rho. And this is the large deviation computation that shows that, you know, if you have exited with this distribution, it's unlikely for you to go down. So of course, sure, if I take the typical value of eta epsilon here, then it's unlikely to go. It's just this computation. But actually, this is not how the exit is typically realized. I mean, if you take some other value of eta epsilon, but so that this is still further away than epsilon. So this deviation is of order that's larger than epsilon times the noise. There's still it's only a small chance to exit. And so the only way to make this exit have a good chance to happen is actually if this entire random variable is of order of magnitude epsilon. So it's an unlikely event. It's an unlikely event. But then, if this is of the order of magnitude of epsilon, then there is a chance to go down. And so we're talking about this, that the second component at the exit, it's supposed to take these unlikely values. And so then it means that eta epsilon has to have this order of magnitude. And if you want to make this, you know, like really useful and to write like a sequence of lemmas that would tell you how this propagates through saddles, then you need local, I call them local limit theorems, meaning that you know, this was done at the level of weak convergence of the distributions of eta epsilon, but you need to zoom into smaller scales to make sense of this. So what is the probability that eta epsilon actually belongs to an interval like this? And this sort of hints at the fact that this probability scales as epsilon to some power. And we can compute these powers. And so this is the main result of that long paper, loosely stated. So it goes like this. So suppose you have a heteroclinic chain, and we are on the plane. And so this chain is a part of the boundary of one cell, right? So the network tessellates the plane into these cells. So this is one cell, and these are pieces of the boundary. And you're asking if your initial condition is it has the scaling that I described in the beginning near this point. What is the probability to exit, you know, to go along all these connections and then exit in the wrong direction, to leave the cell there? And it turns out that depending on the character of the initial scaling, depending on the linearizations at each of those points, there are 3 cases. In a sense, you can describe them all as one case, but let's separate them. So what is the probability to follow this chain and exit at the end? There are 3 cases. One is that this has just positive probability in the limit. That's the old result. But if that probability converges to 0, then what is the character of that convergence? Well, it's either the power law, or it's faster than power. So these unlikely transitions, this is the main result. This unlikely transition, it happens with probability that is epsilon to some power, and we can also compute this coefficient h. We can compute everything. So basically, the main conclusion from this is that no matter what the linearizations are, the result is that the unlikely exit has this power distribution, has the probability of that decays as a power. Now, how exactly does that power come out? So this is a slightly more detailed computation than 2 slides ago. I should ask this question. So if the scaling before the saddle is epsilon to the alpha, how likely is it to exit a distance of order epsilon to beta, where alpha and beta are some numbers? So you have to quantify all transitions between different scales. I mean, you have to define what it means to be of a certain scale. There is a lot of technical stuff that I'm omitting. And so there are these results. If alpha is less than 1, then with high probability you exit at this scale. So that's what is described by the previous work. If alpha is equal to 1, then you still you exit at scale epsilon to the 1 with high probability. So the most interesting situation is when alpha is equal to 1 and rho is less than 1. Then, of course, the typical exit is supposed to happen at the magnitude epsilon to the rho, at distance epsilon to the rho. But if you zoom inside, so if you're interested in a typical exit, so there is a local limit theorem, and this is what it looks like. So probability to be of order of magnitude epsilon to the beta, and in that scaling to land within this interval from A to B. It is described by this asymptotic. So there's this power epsilon in front of this. G is the centered Gaussian kernel, and not the standard one, but you can, if you want, you can renormalize things. So it is. So this is a measure. It's not a probability measure, which you always have in local limit theorems. You're zooming in the standard local limit theorem. So it's an equidistribution result. So when you zoom in, you see the Lebesgue measure. It cannot be a probability measure. So these measures are even sort of worse. They grow polynomially. But anyway, so there is this limit theorem, and this is morally how one can prove it. For this rectilinear oversimplified situation. So this is this case, alpha is equal to 1, rho is less than 1. Alpha equal to 1 means that the initial condition is like this. And this is that formula for the exit location in the second coordinate. I'm just copying it from one of the previous slides. And suppose you want to land within that interval, and the scaling beta is maybe it's not what it's supposed to be. It's atypical. But if you decipher what this means, basically just say this belongs to this interval, and then you just apply algebraic transformations. This is what you end up with, and this sort of says what the limit theorem should be. And so it tells you that it's this random variable that is supposed to have not typical values, but values of this order of magnitude. And in particular, it implies that, first of all, it implies that this is what this probability is supposed to be in the limit. It's power times, so this is where the Gaussian probability comes from. This is this measure, the length of that interval. And also this implies that if you plug in this random variable into this formula, it sort of says that the exit times are abnormally long. What is the significance of this? Right, it's going to be abnormally long because you will plug in this entire expression, and this means that you are not dealing with typical values of this random variable, but much smaller ones. And so you will be dividing by epsilon to that power, and it means that you're going to exit much longer to realize these rare events. What does it mean? I told you that the unlikely, why is the exit in the wrong direction unlikely? It's because the contraction was not strong enough. So you didn't spend enough time to contract. You exited, but you haven't contracted. But if you spend abnormally long time there, then you sort of, that's the rare event, that's the mechanism of additional contraction that brings you closer to the heteroclinic network. and that gives you a chance to exit at the next cell. And this actually happens at, I never have a chance to discuss this slide, but turns out that if you want to exit at saddle number 10, you might need a series of unlikely events that lead to that. So conditioning on exit at saddle number 10 means that you might need to spend slightly longer time at saddles 3, 7, and 5, something like this. And there's a way to compute these, to find these saddles and to see what the distributions are and the corrections and all that. Scalings. So there are new scalings. So instead of following the original scalings in the forward process, the logic is where should you be at saddle 5, how far you should be from the heteroclinic network at saddle 5 in order to be able to exit at saddle 10. And then you might want to do this at several saddles. Okay, so what is the conclusion? For each chain like that, probability to realize cell escape along that chain, it's proportional to epsilon to theta for some theta. So for each chain, you can compute what the theta is, and that means that you can sort of create a whole spectrum of these, or hierarchy of these time scales. I mean, why am I talking about time scale? Well, this epsilon to the theta is the probability, but how long does it take? How long does it take you to see an event of this probability if you have independent trials? It's epsilon to the minus theta, right? If you weight epsilon to the minus theta times log, because you spend logarithmic time at each saddle, then you will start seeing events this improbable, okay? And it means that this gives you a sequence of time scales. So for each of those thetas, you define the associated time scale like this, and then this metastability picture emerges. So if you have a sequence of times indexed by epsilon, and these times are between those time scales, it means that you're going to see a lot of transitions associated with first few thetas up to this time scale, but you will not be seeing transitions associated with longer time scales. And this creates a hierarchical structure of merging clusters. Let me try to explain this with my favorite example here. So I told you initially that with my choice of these rows, at the logarithmic time scale, you're sort of confined to just these clusters of two cells. So which one of the other transitions will be realized? How do you transition between those clusters? So it turns out that with the transition, according to that theory, so if you start here, you can associate a transition rate to this wrong turn, to this wrong turn, and to that wrong turn. If you're back to scaling epsilon to power 1. And it turns out, we can compute all these thetas, and it turns out that this one has, so this provides you the highest probability, which means the shortest time scale. And so what happens is that if you agree to weight for times epsilon to this theta times log, then you will start seeing transitions across these edges, but nothing else. So it means that now these separate clusters at this time scale, they have united, and now there's the new clusters are these 2x2 squares. If you agree to wait longer, then transitions across these vertical edges, they will also become available. So that's this theta. Why is it longer? Well, it's because for that choice of rows, we're now talking about realization of two sequential unlikely events. So you have to do something unusual here to stay longer in the neighborhood of this point, and then also to stay longer in the neighborhood of this point. So the combination of these two rare events, it's a more rare event than just one of those. So transitioning through this is more rare. But once you reach that time scale, you will start seeing lots of transitions between these squares, and the entire strip, horizontal strip, becomes available to you. And then at that point, you can start proving the central limit theorem for the, for how far you deviate typically at that time scale, because this is more or less like, it's not precisely the random walk between these squares, but it's very much like it. And of course, if you agree to wait longer, then the transitions across these edges also become available, and now the entire plane is available to you, but that happens at much longer times. Now, I just wanted to show you that this is not right. So that this is not. I showed you a very high-level introduction to this. I just want to show that there is actual mathematics and theorems in this, and I'm not going to discuss this, but. One more thing is that I wanted to show you a movie. So this is a realization of, it's not a flow, it's, I think, 200 particles, independent runs for 200 particles. And well, so at this time scale that you're going to see, so there are lots of, so mostly they circulate within these complexes of two cells, but then they start making transitions, and so the square is sort of occupied very soon, and then the next transitions, they start happening in the horizontal direction, and well, maybe epsilon is not very small here, and so you already start seeing also transitions in the vertical direction. But this is more or less what the picture is. I also need to zoom into what happens in the beginning. So see, these are typical particles. They, the contraction, the stability coefficient here is less than 1, so they didn't contract enough to exit right away, so they all tend to go up. But so these are these outliers, so they were late. So it's improbable to go down. But what is the mechanism of going down? It's being exposed to the contraction abnormally for an abnormally long time here, and that's how that's what's responsible for creating these transitions. So overall, these are planar pictures, but something like this is also true in higher dimensions. In higher dimensions, there's no notion of cell. And things can be twisted, and that becomes much more sophisticated. But something like this still holds true. And so there is this theme, actually, like more and more systems we see emerging, where the long-term dynamics is not really described by one ergodic measure, right? So what you see here, this is one of the simplest situations that you can have. But what you should be thinking of is that at each of those saddles there's a delta measure, and that's invariant for the dynamics generated by the drift, right? You just stay there. And what happens here is that there's sort of a random walk between these invariant distributions. And so for some time you make transition, but then you spend some time averaging to that invariant distribution. And so that is what Mark Friedl and Lenya Karalov in University of Maryland, they sort of developing a more general theory of this. And at Courant, I'm doing something like this with Ernora Kepa here and Lai Sang-Yang. So we think that this is an important development, that we're going to see more and more systems in high dimensions where a one-sentence description would be intermittent averaging to different invariant distributions. In spin glasses, or everything you talked about, it's sort of like this. So maybe with that, I'm done. Thank you.
Thank you, Yuri. Do we have questions? Of course, I would have loved to see something in high dimension, because of course this is true. This is what the
right.
Story.
So in high dimensions, well, first of all, say you consider maybe this is not your favorite example, but say you have hyperbolic dynamics. So in hyperbolic dynamics, you have chaotic dynamics. So chaos emerges sort of due to this fact that there are lots of periodic orbits and they're dense. And you can, at each scale of perturbation, you can choose some of these periodic orbits. Each periodic orbit supports an invariant distribution, and then you sort of transition between them. And for a while, you do this, and then you transition, and you do something else. And that seems very, very, very generic. Now, of course, this is very planar, and it still took 140 pages to write. Because, I didn't say this, but, we had to use, for that local limit theorem, Malevin calculus, some nested iteration schemes, and it took us 5 years.
Okay, thank you. So let's close this morning session. We start again at 2, right? So see you at 2.